Hi guys, good evening.
Sir, good evening, sir.
Good evening,
Let's
sir.
get started.
Good evening, sir.
And I'm in a class. Can we meet tomorrow? Sure. Yeah. So let's get started. Uh, 1 second. I'm just sharing my here. Yeah. Do you all see my screen? Are you able to see my screen, everybody?
Yes, sir. Yes, sir. Visible.
Okay. Good. Yeah. All right. So let's get started. So yesterday we essentially looking at the last chapter, that is solution to partial differential equations. Solution to partial differential equations, and then we looked at classification of PDEs yesterday. Classification of PDEs. To be specific, we looked at classification of second order PDEs. Okay, we said these are classified based on essentially the characteristic equation, right? We looked at this thing called b square minus 4ac, which is the characteristic equation, and then we have kind of grouped the PDEs or classified them into elliptic or parabolic or hyperbolic, right? Okay, so we're going to primarily look at the elliptic and the parabolic type of equations in terms of how to discretize and solve these type of equations. We are not going to look at hyperbolic equations in this course as such, okay, but some general principles that we develop here will also be, of course, applicable for hyperbolic flow problems also, or hyperbolic equations as well. Okay, so let us now today let us look at the elliptic equations. Elliptic equations. Okay, elliptic equations are characterized, or basically these are typically obtained for steady state problems or equilibrium problems. Okay. For example, if you have, let us say, steady state heat transfer equation. Heat conduction equation. This is an example of an elliptic equation. Similarly, you can also have inviscid. You can also have the potential flow equation for incompressible flows. Also can be categorized as a as an elliptic equation, and you also have the stream function equation. Okay, so these are all few examples of where you may get elliptic equations. Of course, you can also get elliptic equations in other equilibrium problems, and maybe you may get also in structural loading problems. Also, you may get elliptic equations. Okay, because which are basically under equilibrium. Okay, so we said yesterday that few examples of these equations are essentially the Laplace equation, that is dou square phi by 2x square plus dou square phi by dou y square equals 0. That is the Laplace equation. Okay. Similarly, you also have the Poisson's equation, that is del square phi by del x square plus del square phi by del y square equals some function of xy. that is the Poisson's equation. And you also have the Helmholtz equation, which is essentially, if I were to denote del nabla as del square phi by del x square, so this is going to be del square phi plus some alpha square phi equals 0. So that is your Helmholtz equation. So we're going to now learn how to discretize this and then solve these equations. And then we will pick up the Poisson's equation, let us say, as the model, because it is going to be the same for the other two equations as well. Okay, so we're going to pick the Poisson's equation as the model equation, and then going to learn how to discretize this and then solve what are the solution techniques available for the resulting linear algebraic equations. Okay, so before we do that, we recognize that this is basically a two-dimensional problem. So this is a two-dimensional problem because we have both x and y coordinates. So we are looking at a two-dimensional domain, and the domain could be something like this. Let us say this is the domain in which we are interested in solving. So we're going to apply the finite difference method for the discretization. Okay, so so the domain could be something like this, and then where we are prescribing phi values. For example, phi could be prescribed as C1, phi could be prescribed as C2, phi could be prescribed as C3, and then here maybe the normal gradient of phi could be prescribed as some C4 or something. Okay, so these are the boundary conditions that are given. So as we said yesterday, the boundary conditions could be given purely in terms of a Dirichlet boundary condition, in which the value of the dependent quantity is specified, or it could be in terms of a von Neumann boundary condition, in which the normal gradient of the dependent variable is prescribed, or it could be mixed, in which a combination of Dirichlet and Neumann is prescribed. Okay, so these are all possible. I have shown here basically a Dirichlet and then a Neumann combination here. Okay, so we have a Dirichlet, and then there is one Neumann boundary condition that is applied on the top. Okay, so now we have to kind of discretize this thing. That means we have to kind of generate a mesh here. Okay, so that means we're going to generate let us assume we generate a uniform mesh in both the x and y directions. Okay, so that is the mesh we're going to generate. Let us generate a uniform mesh, and uniform mesh with, let us say, delta x is the grid spacing in the x direction, so that is delta x, and then we can also have delta y as the grid spacing in the y direction. Okay, but we say it is uniform. That means wherever you go in the x direction, the grid spacing is always equal to delta x. Okay, that is uniform. Similarly, the grid spacing in the y direction between any two grid points you consider is going to be delta y. So that's why we call it as a uniform mesh. Okay. Okay. So let me kind of redraw this figure slightly here. Okay. Essentially, we have so that is the grid we are dealing with, and then we realize that we are dealing with we are storing our phi values at the nodes. Okay, phi values are stored at nodes. Okay, or vertices. That means we are storing the phi values here. Okay, this is where we are storing. That is our grid, and these are the values we are storing. Nodes are vertices. Okay, so let us call this as, let us say we have the Cartesian coordinate system x and y, and as we move in the x direction, I call this as I. Okay, so we use the index I as we go in the x direction, and we use index j as we move in the y direction. Okay, and let us say we have discretized this on several points. Okay, the points are going from in the x direction, they are going from 0, 1, 2, all the way to m. Okay, that means we have discretized with m+1 points in the x direction. And then in the y direction, we are discretizing is 0, 1, 2, all the way to n. That means we have n+1 points in the y direction. Okay, and out of which the 0 and m will happen to be falling on the left and the right boundary, and 0 and n happen to be falling on the bottom and the top boundary. Okay, that means these are the boundary points. That means I equal to that means j equal to 0 will be this line, and j equals n will be this line. Similarly, I equals 0 will be this line, and I equals m will be this line. Okay, so we have I equals 0, I equals m, and everything in between is going from 1 to all the way to m minus 1. Okay. Similarly, we have j equals 0 and j equals n, and we have I equals 1 to all the way to n minus 1. Okay, 1 to all the way to n minus 1. So this is the these are the boundary points. So we are somehow specified, we have been specified these points, they know the values of the dependent variable on these points. That means we already know somehow, okay? I mean, not somehow, through boundary condition, or we'll be able to calculate them through the other boundary condition. Let us say if it is Neumann, we don't know the value directly, but we can calculate it by including that in the equation. Okay, so that means our unknowns are the points where we need to calculate phi. So phi needs to be calculated at m minus 1 times n minus 1 points. Okay, let us say for the sake of this thing, I can say that phi is also be prescribed on the top boundary. Okay, we will not worry about how this to be included here, this Neumann condition. So let us say if all Dirichlet boundary conditions are given, then my unknowns are phi values are unknown at m minus 1 times n minus 1 points. Okay, so that those many unknowns is what I have. Okay, so that means everything that is in between here, 1 to m minus 1, 1 to n minus 1 is my unknowns. Okay, then we are going to essentially write down our equation. The Poisson equation is partial square phi by partial x square plus partial square phi by partial y square equals f of x comma y. Okay, but we already know that we can discretize this using our finite difference method. So we can approximate the second derivative. Let us say I will approximate this using the second order central difference scheme. Okay, where I can approximate each of these derivatives as phi I. So we know that the derivative, let us say if I want to calculate for some dou square u by dou x square, we know that this is equal to ui plus 1 minus 2 ui plus ui minus 1 divided by delta x square. That is the second order central difference scheme for a dependent variable u to be discretized along in the x direction. Okay, but then we realize that we are dealing with a two-dimensional problem in which we have if this is my ij, this is going to be my I plus 1j, and this point is going to be my I minus 1j, and this is going to be ij plus 1, and this is going to be ij minus 1. Okay, so these are the 4 grid points I have all around the ij point. Of course, we also have these corner points, which are I plus 1j plus 1, I minus 1j plus 1, I minus 1j minus 1, and I plus 1j minus 1. But then we realize that, as we see, these do not enter, the corner points do not enter the formulation in the finite difference method. Okay, so that's what we will see when we use this kind of a thing here. Okay, so we only will be kind of dependent on we will only be dependent on these green points, which are basically I plus 1, I minus 1, j plus 1, j minus 1. Okay, so that means if I were to write this approximation for the for this derivative, we can write this as phi I plus 1, but then we realize that we are applying this at particular j. Okay, so we are applying this equation at a particular j, so I need to carry that j index all along. Okay, and then we have minus 2 times phi ij plus phi I minus 1j. Okay, so essentially I have applied this same equation, okay, what we have written here, and then divided by delta x square. Okay, so that's what we have, and then plus we have the second derivative with respect to y, that is going to be phi I j plus 1 minus 2 times phi ij plus phi I j minus 1, okay, divided by delta y square equals, so that is each of these is an approximation for dou square phi by dou x square and dou square phi by dou y square. And on the right hand side, we have f of xy, that is going to be f of I comma j. That means I am discretizing this entire thing for the grid point at ij. Okay, so with respect to ij, I have expressed the second central difference scheme in terms of I plus 1j, I minus 1j, and ij. And then for the y derivative, second y derivative, we have expressed in terms of ij plus 1, ij minus 1. Okay, so you see that only the green points enter the formulation, the red points do not enter the formulation. Okay, so this is my discrete equation. I can write one such equation. I can write one such equation for each grid point. So one such equation can be written for each grid point. Okay, so by discretizing this thing, we have already converted the partial differential equation into an algebraic equation, right? This is an algebraic equation because this is purely in terms of phi values, which are unknowns, which we want to solve. So our aim is to solve for what is how does phi vary over this entire ij, over this entire domain. That means we want to obtain the distribution of phi. For example, phi could be temperature, right? If you're solving for heat conduction equation, or it could be a scalar or whatever. It is basically diffusing, so this could be the value of the scalar that is diffusing. Okay, so that is the case. Okay, so then what we see is that we can write one such equation for each grid point, which is going to give us essentially m-1 times n-1 equations. Okay, so as we realize that we have as many unknowns as the number of equations. So in principle, this can be solved. In principle, all these equations can be solved together, right, to obtain phi at all grid points, right? So that is what we can do. But then what we realize is that, okay, so okay, any questions so far? Any questions so far, either on today's lecture or previous lectures? Okay, no questions. Let me move forward. If you have any, please feel free to stop me. Let me also try to a little bit simplify. Let me assume, or that our grid is not only uniform, it is also the same in both x and y directions. Okay, let's assume delta x equals delta y, and then what I can do is that essentially I can take delta x, delta y to be the same, and I can send it to the right hand side. Okay, in which case I can write these things slightly differently. I can write this as phi I minus 1j plus phi I plus 1j plus you have phi I j minus 1 plus phi I j plus 1. Okay, so essentially I have written this one, and this one, and then I have minus 2 phi ij and minus 2 phi ij, which will basically become minus 4 phi ij. Okay, minus 4 phi ij equals delta square Fij. Okay, so that is the equation we obtained. For each grid point ij. Okay, now how do I solve for? So we know that we are going to get one such equation for each grid point. So then how do I solve for this thing? Essentially, we end up with a matrix, right? Wherein I can write all the phi values one by one as a column vector. But we realize that we have 2D domain rather than 1D, but then we can still list all our unknowns in one particular order. For example, I can start with increasing order of I, and then I can go to j. For example, if I'm starting from here, I can write phi 1, 1, phi 2, 1, phi 3, 1, phi 4, 1, all the way to phi m minus 1, 1. Then I can write the next unknown as phi 2, 1, phi 2, 2, as phi 1, 2, right? I should write it as phi 1, 2, phi12, then I can write this as phi22, and all the way to phi m minus 1, 2. Then I can keep doing that until I reach phi m minus 1 n minus 1, right? So I am essentially going in an order. That order is that you finish all along x, then you go back and then start with all along x, and then and so on, right? Essentially, we are writing all the unknowns in the increasing order of I first and then j next. Okay. So then essentially, if that is the case, we can write all these coefficients as the coefficients in the matrix, and that matrix is A matrix multiplying with the phi. Phi is the unknown matrix, and you have something on the right hand side. That right hand side is your del square Fij. Okay, so we can put it in a matrix form as A times phi equals right hand side B. Okay, so that is how we can write. But then before we write down this thing, I want you to focus on attention towards one problem, which is basically what will happen when we are close to the boundary. For example, let us say when we are on these points, what we realize is that, let us say we are talking about I equals, let us say if I write the equation I equals 2 to, so if I look at I equals 2 to m minus 1 for j equals 2. Okay, so or let me write it slightly differently. Okay, let me look at I equals 1. Okay, and then j going from 1 to n minus 1. Okay, because 0 is already here. So that means I'm on the y-axis. Okay, I'm just right, here. Okay, it's extending from j equals 2 or 1 to n minus 1, and then I equals 1. Okay, so I am on the on a line that is parallel to y-axis, but it is offset from the y-axis by delta x distance. Okay, I'm on that line, and then I want to write this discrete equation for all the points that are there on that line. So let me pick up something. That means I want to write it for I equals 1 and j going from 1 to n minus 1. 1 to n minus. So that means for all j I want to write, but then only for I equals 1. So how does this equation get modified? This basically becomes I minus 1 becomes 0, 0 comma j, plus this is going to be I 2j plus I 1j minus 1 plus I 1j plus 1 minus phi 1j equals delta square f1 comma j. Okay, so essentially j is going from 1 to n minus 1. Okay, but what you realize is that phi 0j is not an unknown, right? Because this is already known from the boundary condition. The boundary condition was already applied on the left side boundary. So as a result, we already know this thing. So that means we don't have to keep a known value on the left hand side, because if you keep something on the left hand side, it is going to be an unknown. So we're going to send this guy to the right hand side. So we're going to rewrite this thing as phi 2j plus phi 1j minus 1 plus phi 1j plus 1 minus 4 phi ij equals delta square f1j minus phi 0j. Okay, that is how we're going to write. That means what you see is that number of unknowns, number of knowns has reduced. Okay. Similarly, if you're going to let us say, we can also say in particular, we can also say that, let us say if you're applying for j equals 1 out of these all the points, right? If j equals 1, then we know that this is also going to be phi of 1 comma 0 is already a known value, which can be sent to the right hand side. That means we end up with only phi 2j plus phi 1j plus 1 minus phi 1j, okay, where j equals 1 equals del square f1j minus phi 0j 0 1 minus phi 1 0, right? Phi 0 1 minus phi 1 0. That means we are looking at this corner point, right? We are looking at this corner point, which essentially depends on this point, this point, this point, and this point, out of which these 2 points are already known, so they can be sent to the right hand side. And we are only depending on 1, 2, 3. That means this point needs to be evaluated in terms of these 2 values, right? That is how it is. But then, of course, such kind of symmetry will be there if you are here, here, and here, all the corner points, because these point values are known. Whereas in general, for an interior point, you will still have all the 4 neighboring unknowns. Okay, so this kind of discretization, which depends on all the 4 neighbors, including ij, is basically 5, is known as the 5-point stencil. Okay, in the literature, because there are 5 points involved. That is phi ij, phi plus 1j, phi minus 1j, phi j plus 1, and phi j minus 1. Okay. So that's what we have. Okay. So then what I'm trying to say is that your matrix coefficients gets modified as you come closer to the boundaries, and then the known values are sent to the right hand side. Okay. Now we can arrange this in a matrix form, as I said. In which case, what you see is that if I'm going to write it as a matrix form, you see that the central coefficient is going to be -4, and the neighbor coefficients are going to be +1, +1, +1, +1. Okay. That means if I were to write this in a matrix form, so putting this in a matrix form, we obtain, okay, what do we obtain? We obtain a very big matrix, which is going to be -4, 1, and 1, right? Because the other two have gone to the right hand side because they know phi 0, 1 and phi 1, 0 are known. Then the second entry is going to be 1, -4, 1, and then you're going to get a 1. Okay, in between there are zeros. Okay, there are all zeros, and then you're going to get a 0, 1, -4, 1, and then you're going to get 1, and this is going to repeat. Okay, so this is going to repeat like this. You're going to get this 0, 0, 1, -4, 1, and so on. These are all zeros, and then you're going to get some 1 somewhere here, and then the ones are going to again prevail, and then these will also continue. So you got and everything else I have not written here is all zeros. Okay, and then what we have is that we have phi 1, 1, right? That is the first point. Then we have phi, we're going in the increasing order of phi, so this is going to be phi 2, 1, phi 3, 1, and all the way. Then at some point we'll basically get phi once we exhaust all the I points, that is once we reach m-1, 1, then we're going to go to phi 1, 2, then we go to 2, 2, all the way. We go to phi, m-1, 2, right? Then we go to essentially again phi 1, 3, and so on. Okay, so that is how we are arranging all the points. Okay, so you see that the central coefficient, which is phi 1, 1, will get a coefficient of -4. Similarly, phi 2, 2 somewhere there. So this is going to get this central coefficient because you have all other points are written here, right? Okay, so well, phi 2, 1 is also going to get a coefficient, that is this one, right? So not this one. Okay, so this coefficient also will get a phi 2, 1 when you write is also going to get -4. So every point here is going to get a -4 there. Okay, so that is how it's going to be. And then on the right hand side, what you see is that you get del square f1, 1 minus phi 0, 1 minus phi 1, 0. And then for other points, it's going to be only if it is 2, 1, we're going to get del square 2f1 minus, there will be only one boundary, right? Only for the corner point you have 2 points. For everybody else, it's going to be only 1. So this is going to be phi 2, 0, del square f3, 1 minus phi 3, 0, and so on. Okay, so that's how your right hand side vector is going to be, which is a known vector, and this is the unknowns that you have to solve for, and this is the A matrix. Okay, what do we see A matrix to be? We see that A matrix is actually has some kind of a structure with several zeros in between, and then there is some kind of a banded structure. Okay, and this banded structure basically reminds us back, if you go back to the first chapter, that is the chapter on linear algebra, what you see is that this thing is actually a block tridiagonal matrix where you have these blocks. Okay, you have blocks of I, you have another block, you have block of I, and then you get another block of I, block, and so on. So this is basically a block tridiagonal matrix. So this is a block tridiagonal matrix with m-1 by m-1 as the size of the each block. Okay, so size of the each block is going to be m-1 by m-1. I have only shown 3, I've written such as a 3, but this is actually going to be m-1 by m-1. Okay, because you have to include all the points along I as one vector. That is going to be one block. Okay. And so on. So that will be m minus 1 by m minus 1 as the size of each block. And then there are n minus 1 such blocks along the diagonal. Okay. That means together you have m minus 1 by n minus 1 points, or the size of the matrix is going to be m minus 1 times n minus 1 whole square, right? That will be the size of the matrix. That's going to be m minus 1 times n minus 1 whole square would be the size of the matrix, because our unknowns are m minus 1 times n minus 1. So square of that is what is our size of the matrix. Okay. So this is your block tridiagonal matrix. We have already learned how to solve block tridiagonal matrices in the first chapter, that is on the chapter on linear algebra, or on the system of on the solution to system of linear algebraic equations. So this is the application. Okay. Or you can also think of it like, instead of thinking of it like a block tridiagonal matrix, you can also think of it like a pentadiagonal matrix, right? It's a pentadiagonal matrix, but then it is not a pentadiagonal matrix in the same sense as we would perceive, because there are 5 non-zero rows, but then only 3 rows are kind of together. The other 2 rows are separated. They are separated by a distance of m minus 1 points, right? Because this dependency on this point would only come in terms of j plus 1. That means if you are here, this j plus 1 entry will only come once you finish remaining rest of points in x direction, and then come all the way here. So this distance is actually equal to m minus 1 points, right? Because you are traveling the rest of the x-axis and then coming back to that position. That means this entry will only come after m minus 1 entries, right? So as a result, you can think of it like a pentadiagonal matrix, but then only 3 diagonals are adjacent to each other. The other 2 are farther apart. So that is how you can also think of, or you can think of it like a band block tridiagonal matrix. Okay, so in both ways, essentially this can be solved to obtain a solution. Okay, essentially we can solve for this matrix. We can solve for this matrix, and then calculate or obtain phi ij at all points of 1 to m minus 1 and 1 to n minus 1. Okay, 1 to m minus 1 and 1 to n minus 1. We can solve for this. Okay, so okay, so that is the idea. So this is basically if you solve for this, this is going to be the direct method. Okay, so this is a direct method of solution, because we are using the matrices to solve for this. Okay, any questions so far? Okay, we can also use, we don't have to limit ourselves to second order central differencing scheme. Rather, we could even use higher order schemes. For example, I could go for 4th order central difference scheme, in which case my discretization is going to be dou square phi by dou x square plus dou square phi by dou y square equals f of xy. My discretization is going to be much longer, right? So this is going to be minus u I minus 2j plus 16 u I minus 1j minus 30 u ij plus 16 u I plus 1j minus u I plus 2j divided by, going to get something like 12 delta x square, and then you're going to get plus a very symmetric form of this thing is going to be u I j minus 2 minus 16 u I j minus 1 plus 30 u I j minus 16 u I j plus 1, and then minus u I j plus 2 divided by 12 delta y square equals fij. Okay, so what you see is that using a 4th order stencil has now increased your size of the stencil. You're going from I minus 2 to I plus 2, and then j minus 2 to j plus 2. That means you're essentially going not only to the neighbors, you're also going to the next neighbors, right? So that means you are here, you're looking at I minus 2 I plus 1, I plus 2, I minus 1, I minus 2, j plus 1, j plus 2, j minus 1, j minus 2. Okay, you have increased your stencil to get a fourth order scheme. So this will have effect on the matrix you're going to build, right? So the matrix, so this, just like the 5-point stencil, you can think of it just like a 9-point stencil. Okay, so this is 9-point stencil because you are applying it into a 2-dimensional problem with a fourth order central difference scheme. Okay, so but then of course you realize that your matrix A will now have more non-zero rows, because you have earlier you just had 1, 2, 3, 4 rows in which this was a tridiagonal and these two are the pentadiagonal. Now you have more rows, right? Now you have 8 rows which are there, in which case you have 2 plus 2, that means the pentadiagonal matrix is there, and then you would have 2 additional diagonals which are farther apart, right? And you see that actually this one is m minus 1 apart and this one is m minus 1 apart after that. Okay, so of course higher order methods can be, discretization schemes can be although used. The issue is that now higher order is that your stencil increases, and then applying boundary conditions. So as you go closer to the boundaries, you will have difficulty applying higher order schemes, because higher order schemes would want data from the other side of the domain which doesn't exist. So as a result, we won't be able to apply higher order schemes very close to the boundary. So one solution, as we discussed before, is that to switch to lower order schemes closer to boundaries. That means we will use second order CDS closer to boundaries, plus we're going to use fourth order CDS in the interior. Okay, so that is one way possibly in which you can kind of tackle this problem of solving with a higher order accurate scheme, but very rarely we will look at fourth order central difference schemes. Okay, now of course you can extend this idea of applying the second order central difference scheme even to 3 dimensions, right? If you have something like dou square phi by dou x square, dou square phi by dou y square plus dou square phi by dou g square equals some f of x, y, z, then you're going to get dependency on not only 4 points, you're going to get 2 points in the z direction, which is going to basically give you a 7-point stencil, right? That means 6 neighboring points and then 1 point in the center. So this can be also done. Extensions to higher dimensions can also be included. Okay, so all these are fine, but what happens in reality is that usually when you deal with partial differential equations, especially elliptic PDEs, we will get actually the number of degrees of freedom. That means the m by n will come out to be very large, right? You're probably dealing with millions of points or so. So as a result, this becomes very large, and that actually is not a good idea with very large values of m&1. It is not a good idea to use direct methods, although direct methods such as the tridiagonal matrix or block tridiagonal matrices are available. It is still advisable to not use direct methods for very large matrices. If you have small size matrices, a few thousands and so on, you can use it. But for all other things, we would actually practically iterative methods are used. If you take any simulation software for solving elliptic Poisson type of equations, they're going to use iterative methods rather than direct methods. Okay, we will try to motivate you why iterative methods are better for these kind of problems in a little while. So although the solution techniques we have learned can be used, the block tridiagonal and so on can also be used for small sizes. For big sizes of the matrices, for big size of the systems, we're going to switch to something known as iterative methods. Okay, so so let us look at the general iterative methods. How they work and why they could be used instead of the direct methods. Okay, now what we say is that we are writing general iterative methods because we want to learn these iterative methods or develop these iterative methods to solve a times x equals b. Okay, that means we want to solve this ax equal to b, which is basically a linear algebraic system, and and this may or may not be resulting from the discretization of a partial differential equation. Okay, so in this case, it so happens that we are getting Ax equal to b from discretizing a PDE, but the methods we are developing in general need not be coming from, not only applicable for these kind of systems, but if you have in general any Ax equal to b that is coming from any other discretization, you can still apply an iterative method. Okay, so that is the idea. So that is how we are going to develop the iterative methods. Okay, now let us try to kind of motivate how the general iterative methods work, or why they are better than the direct methods for large systems. Is that in case of the direct method, what we do is that, so essentially, direct methods give a solution to, or they give you solution to computer precision, right? Or the round of error that is there. Essentially, the computer precision they're going to give you. That means the solution you're going to go get is exact to the computer precision. Okay, that means in terms of how much small number you can represent in a computer, that is the solution you're going to get with exact solution. Okay, but what we realize is that the systems that we are building or we are obtaining Ax equal to b are obtained, at least in the case of solution of PDEs, they are obtained by applying some kind of a discretization to the governing PDE, right? So in this case, it happens to be the finite difference method is being applied to the governing PDE to get Ax equal to b. That means we are only getting Ax equal to b as an approximation to the PDE. Okay, so in this context, because Ax equal to b itself is an approximation to the exact PDE, it doesn't make so much sense to solve Ax equal to b exactly to obtain a solution, right? That means this discourages us from applying a direct method, because we don't need an answer that is so exact to computer precision that we would need an answer. Okay, rather using an approximate solution to a prescribed tolerance is sufficient. Okay, so that means we don't need an exact answer. We can give some tolerance, and then if we can converge it to that tolerance, this is sufficient. Okay, and then the next thing is that most of the times the matrix A is sparse. Okay, so when it is obtained from the discretization, it is actually a sparse matrix. That means we should make use of the zeros that are there and then represent it in a sparse way, or save the computations. Of course, in the case of direct methods also this is being done, but in the case of iterative methods, the sparse matrices are actually even better, because they will reduce the memory requirements. Okay, which are otherwise there in the direct methods. In some direct methods, if you're going to solve it using a block tridiagonal matrix or something, if you're going to use the pentadiagonal matrix approach, you probably don't have to kind of solve it so much as such. So in that sense, the iterative methods are preferred over the direct methods, because not only the memory requirements are going to be lower, we are not going to get an exact solution, but then we can also say that as we increase the number of iterations, the accuracy of the solution can be improved. That means if you take certain number of iterations, you get some answer, but you can increase the number of iterations so that you get the answer better. Okay, so in that sense, we can increase such that it goes to the whatever is the solution that we desire to the particular tolerance. Okay, so with this motivation, we will look at how a general iterative method is going to work for solving Ax equal to b. Okay, so I'm going to write Ax equal to b, something like this, but then we realize that this is actually A is a matrix, X and B are vectors. Okay, so A is a matrix and X and B are vectors. So the general idea is to split A into A1 minus A2. Okay, such that the following two conditions should be satisfied, such that it is easy to invert A1 and obtain a solution. The second condition is that that the iterative scheme converges as the number of iterations increases. Okay, so these are the two things that we want to be there in a general iterative method. That means we know that, of course, you can obtain from Ax equal to B. You can know that Ax equals A inverse B, but then we don't want to invert this A because A is too difficult to be inverted. We said it is already very costly. We don't want to invert this. On top of that, this A itself is actually very sparse. Okay, we don't want to invert a sparse matrix, that is even worse. So we don't want to do this thing. Rather, we want to now split A into two matrices. We want to write it as difference of two different matrices, A1 minus A2, in which A1 is something that is very easy to invert. Okay, this is very easy to invert. So that is what we want to invert. And then we want to apply an iterative scheme, which will eventually give us a solution. That means I want to write Ax equal to B, but then A is written as A1 minus A2 times X equals B. Okay, so I can again multiply this matrix with vector. So A1x minus A2x equals B. Okay, then what we have is that A1x equals A2x plus B. So let me call this equation 1. Now the general philosophy is that we're going to plug in some known value or guess value on the right hand side, and we're going to obtain a new value on the left hand side. Okay, so that means here xk is a guess value. So we're going to substitute for xk, which is a guess value, and then we're going to once we have this thing, we're going to say A1 times xk plus B is known because A2 is known, B is known, and A1 is something that is easy to invert. So I can calculate what is xk plus 1. Okay, xk plus 1 is simply nothing but A1 inverse A2 xk plus A1 inverse B. Okay, so I can calculate xk plus 1. Now then I can use xk plus 1 and then again use the same equation, calculate xk plus 2. So now we want this iterative process to converge such that the final answer x of some very large iteration number is going to be the final answer. Okay, so that is the idea of the general of any iterative method, whatever you can think of. But then all these iterative methods should satisfy these two properties. That means that A1 is easy to invert and we obtain a solution, and then the iterative scheme converges as the number of iterations increases. Okay, that means as we go, this thing, the iterations should actually converge. Okay, so let us look at the convergence property. The convergence property basically tells us that means here xk plus 1, I'm putting in parentheses here to differentiate that this is not an exponent, but this is the iteration value, equals A1 inverse A2 times xk plus A1 inverse B. Okay, that's what we have. Okay, so this is what I have. Let me write this as equation number 2. Okay, so if I subtract 1 minus 2, what am I going to get? I'm going to get essentially x minus xk plus 1. So let me denote what is the error involved. Error involved is, if I were to denote as epsilon k, okay, at any time step k, epsilon bar is going to be x minus x bar k, or x bar minus x bar k. Let us say if x bar is the exact solution, it is going to be x bar minus x bar k. Okay, that is the error at any step k. Okay, then if I'm going to write 1 minus 2, what am I going to get? Essentially, I'm going to get A1 times x bar minus x bar k plus 1 equals A2 times x bar minus x bar k plus B minus B is 0. Okay, so what I obtained is by subtracting 1 minus 2 is A1 times x bar minus x bar k plus 1 equals a2 times x bar minus x bar k is what I obtained. Now we know that this is basically the error at k plus 1 iteration equals a2 times this is the error at kth iteration. Okay, so that is the error. That means I can write error at k plus 1 iteration equals, by bringing a1 to the right hand side, I can write this as a1 inverse a2 times error at the kth iteration. Or we can also write this as error at the kth iteration equals a1 inverse a2 to the power k times error at the 0th iteration, right? So if I were to repeatedly apply this thing, I can obtain this formula. Okay, so what does this mean? This means that we want, as k tends to infinity, we want epsilon k to tend to 0, right? We want the round of error, we want the error to basically to go to 0. And we know that from linear algebra, this can only happen if rho, which is equal to modulus of lambda I max, is less than 1, okay? Less than or equal to 1, where lambda I are the eigenvalues of a1 inverse a2, okay? So if we calculate eigenvalues of a1 inverse a2 and we take the maximum eigenvalue of that, if that is less than or equal to 1, then we know that when you raise that to the kth power, that is going to, then the error is going to decay to 0, okay? So which here we call rho as the spectral radius of the matrix, and it is going to give you, it is going to control the rate of convergence of the iterative scheme. Okay, so so essentially what we now know is that whatever we do, this eigenvalue of the a1 inverse a2 should be less than or equal to 1, or the maximum absolute eigenvalue. Okay, that should be less than or equal to 1, so that the method converges. Okay, so that is the idea. So we have with these things, we have a couple of different methods which are known as the Jacobi method and the Gauss-Seidel method, and then there is something called successive over relaxation, which are all the iterative methods that we're going to see in tomorrow's class. Okay, so we're going to see the Jacobi method, and then the Gauss-Seidel method, and successive over relaxation. How does these methods work? We're going to see them tomorrow, which are all the iterative methods. Okay, so any questions, anybody? I'm going to stop here. We are out of time. I'm going to stop here, guys. Any questions? Any questions, anybody?
No, sir. Everything is fine, sir. We have go through it and come back to sir tomorrow.
Okay, fine. Okay, you can, let me know.
Sir, when we can have the formula sheet to you, sir? You can handle
Whenever you guys are ready. Let me check what is the last date for me to submit the question paper to them.
Okay.
If you can give me a day before that, I can just put it together with the question paper.
Okay, because we are in the 5th chapter now, sir. So
We are yeah.
Once we finish the 5th chapter, then we can know the 5th chapter formula also.
Yeah. So you can probably work on all the equations till now, and then pending the 5th chapter.
Okay.
You can keep adding whatever we are doing today, and then I think so. Essentially, we'll finish by next week. That's what we are targeting at.
Yes.
Yeah. So next week. So then I think by next week you will have pretty much all the formula. Maybe by end of next week, if you can give me, that will be great. I'll anyway confirm you the exact date. Okay.
Right, sir.
Yeah. So I'm hoping, I don't know, we'll see. I think by tomorrow we'll decide if we want an extra class on Thursday and or not. Okay. So in the worst case, we'll have one extra class this week and one next week, something like that. Otherwise,
Yes,
we'll have only one extra class either this week or the next week, something like that. We'll decide.
We will do it this week itself, sir. That should be better.
Yeah. Okay. Fine.
Right, sir.
And it can be at the same time, right? I think that is what is convenient.
Yeah, sir. Yeah,
Yeah,
4 to 5.
Sure. Yeah.
Thank you.
Okay,
sir.
guys. Yeah, I'm going to stop here. Unless if you have any questions, otherwise we can call it a day. Okay, thank you, guys. Then I'll talk to you tomorrow at 4
Thank you.
o'clock. Thank you. Thank you.
Yeah, thank you, sir. Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you very much. Yeah.